And we are back, everyone. So what we are going to focus on, and a lot of these will be looking at forces, resolving forces, resultants, and systems of forces, but in these particular statics problems, one of the common threads and the things that we are going to take into account and focus on in this particular part of the lecture is friction. Now, there are many different types of friction. So you could have friction basically from screws. So basically on that thread, you can have rolling friction. So when I have a rolling tire, it deforms essentially the body here. I can have bearing friction. I can have, when I put a wedge between, or try to lift off certain bodies, I can have friction on those wedges. There are a myriad of different types of friction, but one of the most important and predominant types of friction is what we are going to refer to as dry friction, or Coulomb or Coulombic friction. So that just occurs between two contacting surface when there's no lubricating fluids, i.e. when we don't say it's a smooth surface or it's a lubricated surface. So we have to account for that dry friction. So when or how does this occur? Let's go ahead and let's take a look at it. And actually we have a handy little diagram here. This is a diagram showing our coefficient of friction versus our force. So if I have a surface, let me go ahead and draw that right here. So I have a surface, I have a body that's on this surface, and we can see here I'm going to have at my centroid, there's going to be some weight. Let's go ahead and draw this a little bit nicer. A weight. There's going to be a restoring normal force here. Let me draw this normal force. And let's say I start to apply some external force right here. Now, obviously, these are two contacting surfaces. I did not say they're smooth surfaces, so there is going to be some friction here. Now, one of the most important things when we're talking about dry friction is the following. Actually, let's go ahead and let's see if we can Actually, we'll go ahead and write it up here. So the first, our friction, or the frictional force. So friction, dry friction, will be tangent to contacting surfaces. So it has to be tangent to those contacting surfaces. And the second, it needs to be opposite to the direction of impending motion. And this is described in the notes and in the slides as well. So that is our condition. So if I apply a force like this, that body will want to move in this direction here. Again, we should always, whenever we have a problem like this, y, x, plus, for the counterclockwise. So the impending motion is in this direction. So if I need to be tangent to this surface, my friction will act tangent. So in this direction, or actually in this, this is tangent to my surface here, and it needs to oppose the direction of impending motion. So it'll be like this. We've satisfied those two conditions. And that makes sense, right? Because if, again, friction is going to oppose that impending motion. So if there's not a large enough force applied to overcome this friction, we are going to be in static equilibrium. Now, the question you may have is, well, what's the magnitude of that friction or that force? And we can also describe our frictional force here is just going to be equal to our coefficient of friction times the normal, the magnitude of that normal force. So that is our definition of friction. But what about this coefficient of friction? Because again, if we're in static equilibrium and some of my y forces will, basically sub to zero, I need this to be equal to this in this system. So this must be equal to this force right here. And again, that's like an external force. So that is our condition. Now, if I just initially, and you can kind of see here, if I initially have a relatively small applied force, I will have a correspondingly small coefficient of friction. The normal, again, the magnitude is determined solely by this. so my coefficient of friction will be lower as well. So, but I'm still balanced out here. As I increase my force, and actually we can go ahead and scroll down right here. As I start to now, for this point right here, as I increase my force, my coefficient of friction also increases. And this continues until I reach a maximum. And this maximum is my static coefficient of friction. So that's my maximum value or limiting, value of static friction. So that is typically represented if I look at F static, US times my normal. So that is the maximum value. If I have an applied force that is greater than F sub S, now I am going to break static equilibrium, i.e. the sum of the forces in the x direction equal to 0, sum of the forces in the y direction also equal to 0. So if I go beyond this, now that will move, and then we're in dynamics territory. But we're not going to get into that today. So this is essentially our limiting value. And you can see in the figure here, the coefficient of friction drops, and we reach this kind of plateau of our, basically this is our coefficient of kinetic friction, UK. So that's this little line right here. And you can see now, we are, basically, we're not balanced. This force is larger, or this magnitude is larger than that magnitude, so we don't sum to here. So again, we're in dynamics territory, which you'll get into later in this class. But today we are not going to violate that. So we need to, and the problems that we're going to work with today is essentially seeing, well, what's the largest force, or what's the largest coefficient of, or what is the coefficient of friction that I need to ensure that I stay in static equilibrium. So again, that is what we need to account for in these systems. We need to make sure that when we, look at and start to understand or apply or consider friction, we have to make sure that we do these two things. Friction is tangent to the contact surfaces, and it must oppose the impending direction of motion. That is our charge today. And then we're going to do a lot of cool problems. And specifically, next time, I'm going to tell you all a story of when I had to pull a car 0.7 miles in the middle of January in middle of nowhere in Ohio when it was freezing. But that story for next time. So hopefully this has been helpful, and I will see you next time when we're going to start to calculate problems. So be ready, and we'll get going. Thanks. See you then. Bye.